Hi everyone, I'm delighted to be here today. My name is Cordula Weiss, and I'm very much looking forward to discussing some of my favorite topics with you today. So my background actually is in respiratory drug delivery. For a couple of years I was looking into the crystallization of compounds or particles that would be inhalable and alleviate the symptoms of asthma. Now, crystallization, but what I'm having here is chocolate. Doesn't make sense, but I think at the end of the day it will, because crystallization is actually quite an important thing when we do talk about chocolate. I am personally an absolute chocolate addict. I eat any kind of chocolate whenever I can. Doesn't matter if it's dark chocolate, milk chocolate, anything. But what's important to me is that I get this very exquisite, very unique chocolatey taste, smooth texture, has to melt and just have this very, very special, unique taste that I suppose quite a few of us crave. I'm definitely one of them. Now, crystallization in chocolate. The reason we get this smooth texture and this shiny surface is actually because of crystallization. So there's a whole load of science behind making chocolate, manufacturing chocolate, and the whole process of making chocolate has to do a lot with getting the crystallization right. Putting the chocolate aside, there's actually loads more about crystals. Crystals are everywhere around us. Crystals play a huge and extremely important role in our lives. And of course, that's not just limited to, the ice crystals, food such as chocolate. It also relates to the treatment of diseases. Just think about respiratory disorders, inhalation, dry powder inhalation, all based on crystals. But even more importantly, it was a crystal that told us so much more about the secret of life. And when I'm saying that, I'm actually talking about one of the hidden figures in research. And that person, she was born on the 25th July 1920, so it would have been 100 years in 2020. Unfortunately, she died quite young. She died in 1958 because of cancer. And this person played a critical role in the discovery of DNA. The way she did it is she refined her own X-ray machine, X-ray diffraction. She put loads and loads and loads, many hours of work into getting very good X-ray diffraction images of crystalline DNA. She looked at strings of DNA, and one of the forms she looked at is what we now know is this double helix structure of the DNA. She put about 100 hours of X-ray diffraction runtime into getting photograph 51. That photograph 51 was essential in the discovery of the structure of DNA. The lady I'm talking about is Rosalind Franklin. Herself and her PhD student Raymond Gosling, they were working on identifying, analyzing strings of DNA. But Rosalind Franklin, for a very long time, was not acknowledged in any way for her contribution to that discovery. What happened is that her colleagues, Wilkins, Watson and Crick, they took her photograph, they used her data, where she spent hours and hours of work. So they took the data, found the structure of DNA based on Rosalind Franklin's data, and according to, there's an anecdote going around, so rumor has it, that Crick even said in a pub that he has discovered the secret of life. So they were aware of the importance of that discovery, but in no way did they acknowledge Rosalind Franklin's contribution. And in 1962, the three men, Wilkins, Watson and Crick, they were awarded the Nobel Prize for the discovery of the structure of DNA, of this double helix structure. Rosalind Franklin died in 1958. That was 4 years before her three colleagues even were awarded the Nobel Prize for the discovery of the helix structure of the DNA. It is now acknowledged that Rosalind Franklin was the one who delivered the crucial evidence that was needed to analyze the structure of DNA. Now, I know I've been mentioning those words, those terms, crystal and crystallization, quite a lot, just right at the beginning of this talk. Let's clarify what exactly is actually a crystal and what is crystallization. When we talk about crystals, the first thing that comes to mind very often is an ice crystal, snowflakes, sugar, salt, chocolate now, I suppose, as well. But what exactly makes a crystal a crystal? So it's not just a solid. I'm sitting here on a wooden table. It's not a crystal, but it's a solid. A crystal is a solid, but inside that solid, there's a certain arrangement, an incredibly precise and regular lattice, a 3D structure of atoms or molecules. They are arranged at very well defined angles, very well defined 3D lattices, and that stretches across the whole crystal. So it's extremely regular over a long distance. Crystallization is the process of forming a crystal, of growing a crystal. Crystals literally grow because what happens very often is that you have a small particle, like a dust particle, and on that the first atoms, the first molecules attach. Onto those again, the next molecules, the next atoms attach, and all that in a very regular pattern. So literally the crystal grows by more and more atoms or molecules attaching. The question now is, why don't crystals just constantly grow everywhere around us? Like, I'm here in a room, there's loads of dust, but not that many crystals. They don't just form and grow and grow and grow. What we also need, and again, this is just one example of how we can grow a crystal, how we can produce a crystal, how they can be manufactured. I suppose it is the most common one, is the one that we can all relate to, because it's a way, or it's a method that we use every day without even realizing. Now let's assume we have a pot of water here with a fixed volume of water, say a liter of water, and into that liter of water we add a tablespoon of salt. We stir and the salt dissolves. It's not visible to our eyes anymore. We add more salt, we stir, it dissolves. We add more, stir, dissolves, and so on. Until at some point you notice there's a little bit of salt left over. We can't dissolve it anymore, and exactly at the point when the salt stops dissolving, at that point we have a saturated solution. Now if we add more salt, we get a supersaturated solution. Now you can of course say, oh yeah, what if I increase the temperature? What if I heat the solution up? It will dissolve. And that's right. Let's assume you're heating up your solution from room temperature to 50 degrees. And yes, the salt will dissolve. So you might think, great, 50 degrees, all dissolved, I can go back, turn off the heat, let it cool back down to room temperature. But I think we all know what happens when we cool it back down to room temperature. The salt again reaches, or the solution again reaches the supersaturated state, and at that point the salt will start to precipitate. So precipitation is when the salt is forming from that supersaturated solution. Now back to chocolate. I haven't mentioned that for a while. Chocolate actually consists of cocoa butter. Surprise! So the darker the chocolate, the more cocoa butter there is. Cocoa butter forms 6 different forms of crystals, and only one of those 6, form 5, is the one that we want. Form 5 is the one that gives us the smooth texture, the shiny surface, and it's the one that makes chocolate what chocolate actually is, and that amazing taste and smoothness that we like about chocolate. How do we get form 5? We use a process called tempering. Suppose the name says it already, tempering, temperature. We heat it up. We melt chocolate, let it cool down again, but in an extremely precise and extremely controlled fashion. You've probably all done it at home. We're heating up chocolate, we're stirring it, we're heating it up, it's melting, it's great. We let it cool down and it's just not the same as it was before. That's because not just form 5, but a couple of different forms are forming. So form 5 of cocoa butter plus additional crystals that we don't want. And how do we get around this? The cocoa butter crystals, form 5, the one that we want, it forms at 35 degrees. So we melt our chocolate at about 45 degrees. Then let it slowly cool down to mid-20s, room temperature. And that's it. It's actually not it. I was just saying, when you cool it down, different crystals are forming. So of course, when we heat it up to 45 degrees, let it cool down, we do pass the 35 degrees where our good crystals, the ones that we want, the ones that give it the smooth texture and the surface, the shiny surface, they do form at 35 degrees. But then at about 27 degrees, we have additional crystals forming, and that's the crystals they're called form 4. And they're not great. We don't want them. So in this tempering process, we have to destroy those crystals that we don't want. Makes sense. Now, guess what we do? Because we know that form 5 is forming and melting at around 35 degrees. Again, the exact temperature very much depends on the whole composition of your chocolate. And we know that the form that we don't want, form 4, forms and melts at 27 degrees. So in order to destroy form 4 but keep form 5, you're going to heat the whole chocolate up again, but only to 29 degrees. Because at that point we know that the crystals that we don't want, form 4, are destroyed, but the good ones, form 5, they are not melting yet, because we are still 6 degrees below the melting temperature of the good crystals. And this is like a very short description of the tempering process. There's loads more steps, of course, involved, and it's not as easy as just, heating it up and down, because chocolate does not only consist of cocoa butter, but so many more ingredients. And I'm pretty sure that most chocolate manufacturers have their own little secrets to achieve that specific smoothness and taste. But try it at home, get some chocolate, see how you get on. It's a lovely experiment to do at home. And again, keep in mind that white chocolate, milk chocolate, dark chocolate, they all have different amounts of cocoa butter, so they all might behave slightly differently. What all chocolates have in common though, and I'm sure you've noticed that at one point or another, is that after a while something we call blooming occurs. It's when the chocolate turns kind of grayish with white spots, fat blooming. And this is what happens over time, because form 5, the good one, is actually not the most stable one. That would be form 6, and this is what we can then observe.